Introduce Andreas Zeller. Andreas is a faculty at the new center, CISP Center, and also a professor of software engineering at Southern University. So Andreas is very well known in the software testing community, and so he's an ACM fellow. He recently just won the ACM 6 of Outstanding Researcher Award, and that's a huge accomplishment, and that's also a huge recognition of what Andreas has done. So he has made fundamental contributions in many areas, including like his work on delta debugging, and actually my group has benefited quite a bit from that work on compiler testing. And also he has kind of like done seminal work on mining software repository, and also his work on Fuzzing has had a huge impact, found like thousands of bugs in JavaScript interpreters. And so with that, I welcome Andreas back to Zurich, and let's hear from Andreas.
Thank you, Zhendong, and I guess you can all hear me very well at this volume. Great to see all of you. I hope to keep you awake for the next 45 minutes. I hope you had a great dinner tonight. The organizers and the speakers certainly had. So a bit of context. Context, yes, this is Europe. We are somewhere over here. Let me put up the border here so it's going to be a bit easier. Should be around here. This little 2x2 pixely thing in orange, this is the state of Saarland. This is where I am, and precisely in the city of Saarbrücken, right on the border to France. And this is the building I'm in, which happens to be our all-new CISP Research Center. This is the Center for IT Security, Privacy, and Accountability. And it has made quite some waves in the last year, because this center is set to become a new so-called Helmholtz Center, officially by the beginning of next year. And this one building in which we are right now will be complemented by approximately 5 to 6 more buildings, because it will grow from right now about 100 researchers to 500 researchers. So that's approximately 100 faculty and 400 PhD students, with a base funding of 50 million a year guaranteed for the next decades. So the state of Germany invests heavily in IT security, and yes, we are hiring. If you can connect, after finishing what you're currently doing, if you can connect your work to security in some way, say I'm working on secure programming languages, secure program verification, secure analysis, yes, sure, let us know, and we'll be very happy to hear from you. Okay, so what am I doing in this very building? My main work these days is on test generation, or also known as fuzzing. Fuzzing is a super easy technique. You create a program that creates random inputs, and you feed these inputs to a program of choice. And since every behavior of a program can be induced by an input, if you just fuzz long enough, you will get all behaviors, including the bad ones. Long enough here means, well, till the end of the universe, typically, but if you're lucky, you can find quite a number of errors very quickly. And fuzzing is, of course, an old technique. It's been around for at least 30 years. When Bart Miller came up with the first fuzzing tool, this actually was a student assignment, and an implementation of fuzzing in the style of Bart Miller, that's 10 lines of code. When he did this about 30 years ago, he found that 1/3 of all Unix utility at the time would crash or hang when subjected to fuzz input, which was quite a thing at the time. Imagine if something like this happened today, if you found an attack that would tear down 1/3 of all programs. That was quite a thing. And our interest there in fuzzing techniques, today this doesn't happen anymore. Try this today. In particular with GNU tools, you have very little chances of getting them to crash, because they have been fuzzed quite a lot already. Our interest these days, however, is mostly in so-called grammar fuzzing, which means that if you have a parser at the beginning of your program, which checks inputs for validity and if there are constraints for validity, with fuzzing you will typically find errors in that very parser, But if your parser is well done, for instance, because it's generated and well tested, you will have a hard time getting deeper into the program if you just feed it random inputs. If you feed random inputs to a compiler of choice, well, you're going to find errors in the lexer, if at all, but probably not get anywhere deeper than that. In order to get deeper, you need inputs that are syntactically correct, such they can bypass the checks of the parser and get to the actual functionality. 6 years ago, we built a tool that would do precisely that. It was called LangFuzz. This was a fuzz tester that would take a grammar and build inputs from it. We built this for JavaScript, and the fun part about LangFuzz was not only would it use JavaScript, not only would it use the grammar to generate inputs, using it as a producer, but it would also use the grammar to parse existing inputs. And in particular, it would be able to recombine those existing inputs into new inputs. And if I tell you that the inputs we used were actually past bugs and past fixes, then you can inputs that would cause bugs in the past. So it would cause, suppose you're immune to the common cold, you're immune to measles and whatnot, so this has been fixed. Now we take random strands of measles, random strands of common cold, recombine them and feed them. This is what we did here with LangFuzz, and this was pretty successful. This is the grammar. Well, I'm talking to a programming language audience here, so you know what a grammar is. I'm going to skip over that. This is one of the typical inputs we would generate, and this input would happily crash the Mozilla interpreter here with the last line when being read and executed. At the time, this was lots of fun, because we found plenty of bugs very quickly. My student, Christian Holler, who did the by far bulk of this work, gained 18 Chromium Security Rewards, 12 Mozilla Security Bug Bounty Awards in 9 months. This is how long he ran the tool for our experiments. And there's another number, though, that is more impressive. In the first 4 weeks, he gained $50,000 in bug bounties and propelled himself to the top of all security charts. So he made the top of the leaderboards in reporting the most bugs. That was lots of fun. People sometimes ask you, how much did he do in the next 4 weeks? This is unknown, because after 4 weeks, Mozilla immediately hired him away, and he now has a very nice salary at Mozilla. And his main job is keeping his program running. He runs LangFuzz on Mozilla all day long. He also has given LangFuzz to Microsoft, so Microsoft runs this for Microsoft Edge. In his spare time, which actually is plenty, he runs LangFuzz on Google Chrome and still brings in bug reports. So if you use any of these browsers, so far LangFuzz has found 2,600 confirmed and fixed bugs in JavaScript. So if you run any of these browsers and they work and they're secure, well, we had some say to that. So our tool did its part in order to make that work.
So, Andreas, what is the y-axis there?
The y-axis is the number of defects we found over time, if I recall this right. This is
if this is 1, 2, 3, why are there not jumps? I mean, then did you find...
It's cumulative. It's cumulative, if I recall this right.
Yeah, but why? I mean, it sounds like at some point you had 1.7, 1.8, 1.9 bugs.
Yeah, that's very interesting too. I just noticed that. I just noticed this as well. This is a slide I happily snatched from Christian's presentation at the time. So yes, thank you for actually looking at the numbers. That's a good thing. Most people are totally mesmerized by this number. I don't look anywhere else. But you're actually able to spot the gorilla in the background. Okay, good. One thing, of course, is that in order turning a grammar into a producer is something that, at least in principle, is well understood. But the thing is, in order to test this way, you need a grammar in the first place. And developing such a grammar, in particular if you want the grammar to be useful not only for producing but also for parsing, is actually quite some time. So Christian, the guy who did the work, it took him 3 months to build an appropriate JavaScript grammar. Not only, as I said, not only a grammar that would be useful for producing but also for parsing. And you cannot simply take a grammar from an existing It cannot simply take a grammar from an existing JavaScript interpreter because it's heavily interwoven with the rest of the program. All of this is rather difficult. And this has been one of the major obstacles to grammar-based testing. You need to invest first in specifying what your file format is. So we have been investing quite a lot in the last years to build tools that would be able to learn such grammars, to automatically learn from a program what the input language is. We assume a program simply takes one single stream of characters. That's a simple abstraction, and we assume that we can characterize this stream as a formal language, regular expressions, grammars, you name it, and we want to be able to learn such a language from the program and its executions. So one of the easiest ways that we have developed is as follows. Let's assume we have a program that takes a URL as an input and then processes this URL. If you actually look at the constituents of this URL, turns out that all these individual parts, the protocol, the host name, the port, user, password, you can specify logins in URLs. Don't do that. It's an anti-pattern, but you can do it. The page request and the delimiters, all of these parts go through very different paths in the program as they're being processed. The protocol, for instance, determines how the rest of the string will be parsed. The host name will go to some DNS resolver and be turned into an IP address. With this IP address, the program is going to open a socket at the port, and then it's going to send the login and the page request over the connection to that port. So each and every part in here ends up in different variables and ends up in different functions. And this is the idea that this is the observation that we can make use of in order to derive a grammar from the string. So what we want to do is we want to find out for each and every character of the input where this character eventually ends up, in which variables it gets stored, and in which function it eventually ends up. So in other words, we want to do a dynamic tainting. That is, where is the flow of the characters through the program execution? There's two ways for doing that. One is indeed dynamic tainting. This is the good way. This means that we actually wrap each character, we tag each character with information that relates to its origin. But we also have a simpler mechanism that simply goes and takes a snapshot of the memory and simply checks which variables, which string variables in particular, hold parts of the input. The first technique, we have implemented both techniques. The first technique is more precise but pretty demanding, building a wrapper around every character and making sure that every access to that character is actually properly tagged, and everything is pretty demanding, in particular if you go deep into the system. Recognizing inputs is much easier. This is something that you can actually do without having to instrument the program. Let me show you how this second technique works, because it's really straightforward. You start with a very simple grammar that simply consists of the one single string that you have just passed as input. This is a grammar. Boom, problem solved. Okay, this is not what we want to have, but well, technically it's a grammar. It's a grammar that consists of one single string. Now we want to refine this, and the way we do this is we actually go and extract the variables of the program and their values, and we check for variables that actually contain substrings of the input, which we know. And let's assume we found this is the set of variables we found that actually contain parts of the input. And now what we do is we apply two simple rules. For every variable and a value that we find in here, we replace the value we find in here by a symbolic reference to that variable and introduce an appropriate variable in our grammar. So here's an example. This is the variable not netlock, which you find down here. Now we can go and replace the string that's matching up here by netlock, and we add a new rule to that. Now we have identified the netlock component. We can do the same for the scheme. Here we have a scheme. Now we do the same for the path, and now we have a path. And we do the same for the fragment. We do the same for the fragment. And we have a URL down here. Actually, all these variables so far have been very aptly named. This is very nice because this makes the grammar very readable. Up here, we can't have that, so for some reason the URL is a misnomer here, but still, we do have a grammar at this point. This still reflects the very same string as we have seen before, but now we have decomposed it into individual constituents, and you can see the structure in here. Yes? That's true too. There's two occurrences of path, and you could also have a $URL up here, and URL being defined as path, and path being defined as path. We don't have everything under control here because we rely on the variables as they are named and as they are used by the programmer here. But both structurally as well as from the natural language semantics, I think we are on a good path here. And this is actually something that is rather easy to implement. Say in Python, and I'd like to give you a short demo of that. So let me go into my neat little super duper program here. 1 second. Where is the magic key? No, this is wrong. So 1 second. Here we go, and I need to turn on mirroring such that you see what I see too. This is here. This is a new laptop, so I'm still struggling with parts of it. This is exactly what I want to have. Here's me, and here's my beautiful environment. This is a Jupyter notebook, and here is the actual code that does this grammar mining. We do have a couple of inputs. I hope this is large enough. Can you read this at the last row? Okay, good. You have better eyes than I do. And what we do here is first we go and track the individual variable values. Fortunately for us in Python, this is super simple. What you do is you define a tracing function, which gets called for each and every line of the program. And in this tracing function, you can very easily access all the variables, which you get here. And you can go and extract all their values. All these are Python objects. And this is all there is. What we do here is we check whether it's a string, and if the length of the string, if it's more than 2 characters, and the value occurs in the input, then we save the values. Then we save the variable and its value. And that's all there is. Python is an absolutely great language for doing dynamic analysis. That's what I like to point out. Doing a similar thing in Java or in C will require you probably weeks of implementation. In Python, you can do this in, well, if you don't know about it, it will take you an hour. If you know how it is, it's 5 minutes. Now you set a trace. This is the function that sets the trace, and then you call the function that you're interested in, which in our case is URL parse. Now I can go and actually execute these individual parts. Let me see what happens here. So here we execute the whole thing. And here's the variables which you get. This is URL and scheme and netlock. These are precisely variables as we've seen them before on the slide. Now I can go and extract a grammar. And in order to extract a grammar, this is the function that actually does this magic of doing the replacement and checking whether parts are actually in there. You've seen this before. Here I go, and this is the grammar I get. Start is a URL. URL is a scheme, netlock, query, fragment. Scheme is HTTP, fragment is reference, query is path. This is precisely the same values as we've seen before. Now I can do a similar thing for another input. Let's use this one. This is cispa.saarland 80, and you see here the URL is now a bit different. You have scheme and rest here, but still the structure is clear. I can get another one. This is fuzzingbook.org. Scheme, netlock, fragment, all up here. I can also put in ETH Zurich, for instance, just for the fun of it. But these are all grammars that you get. Now, technically, these individual grammars are still grammars that represent one single input. What I can do next is I can merge these grammars. And by merging these grammars, this simply means that for each and every symbol in the grammar, I merge these grammars by determining alternatives. So start here is always URL, but URL is either scheme netlock query fragment or scheme rest or scheme netlock fragment. The netlock is very different. It's a different host name each time. And by merging these grammars, I create alternatives out of these. So if I do this, I can get the merged grammar. Now I create a grammar for all 3 inputs. And now you see that netlock has these 3 values: user pass, google.com, cispa, and fuzzingbook.org. And now now I have these alternatives. And since I now have these alternatives for each and every symbol, I can go and combine them as I wish, simply by using the grammar as a producer again. And then I get all sorts of combinations here of schemes, of URLs, of paths. All of these are now happily interspersed with each other. And the more inputs I put in there, the more variation there is, of course. This is a very simple approach. The whole thing, without any additional code, so including the production even, is approximately 200 lines of code. This is what it takes to learn a grammar from existing inputs. Well, if you are working in Python, that is. So this is one of the simpler algorithms that we've built. We use these for teaching. But we have also built a larger grammar miner. This works for Java programs, and this has a couple of extra bells and whistles. In particular, it uses active learnings to find out which parts in the grammar are repeated, which parts are optional. To find out whether a part is optional, what we do is we leave the part away, and then we check whether this is still a valid input. Yes, you had a question?
Just a quick question. Could you explain a little bit why do we want to learn these grammars? I mean, for JavaScript, of course, I mean, the grammar, do they have some sort of like a YAC or Bison sort of grammar that you could just use? And also for the URL, I guess there's some sort of specification you could just use, right?
I could use the specification, of course, but then I have to manually go and turn the specification into an actual grammar. If I can learn this specification from a program, I'll be much happier. And there's plenty of programs around for which no formal specification actually exists. I think that I remember a quote that 85% of all parsers in industry are handwritten recursive parsers, meaning that you'll have deep trouble finding a specification for the grammar in the first place. And if you want to fuzz these programs, you have to, traditionally, you have to reverse engineer what happens in these programs and figure out what the correct input to a program is. This is an interesting obstacle to testing, actually. And if you use any test generator, say like AFL or likewise, on a program of choice, you'll very quickly find out that, test a URL, for instance, 95, 97, whatever % of all inputs are simply invalid. By far, most inputs are invalid. So many inputs don't make sense at all.
Right. So your goal is try to make this more general, right? For JavaScript,
exactly.
So you probably don't need to do
so
it.
There's multiple reasons for us to extract such grammars. One is reverse engineering. This is fine. But first and foremost, we want to use these grammars for better testing. Once you have a grammar, you can test like crazy. You can test with lots and lots of valid inputs, cover all the individual parts very quickly.
I'm just curious to hear what your experience is on the fact that often these errors come from bits where the spec says something else than was implemented. And then so if you follow the implementation to infer the grammar, then you kind of fall into the fragment that the implementation handles well. And so there might be a large number of bugs that are like in the gap between implementation and spec.
Actually, this is why we focus a lot on readability of these grammars that we get. And I'll show you more examples in a second. Because if you read these grammars and you know about the program, you can very easily find those gaps. You can also take, if you have an existing set of inputs that you know are valid and or that have been processed by other programs, you can compare them against. So you can compare them against the grammar by simply parsing them. You can extract such grammars from multiple implementations and compare them against each other. There's multiple ways you can detect such differences between what the program is supposed to do and what it actually does. And these techniques of active learning, for instance, also go and insert variations into the program in order to find out whether there's more to learn, and consequently also explore the surroundings of the grammar. And indeed, we have found programs that accept way more than they should, and this is an error. Okay, let me show you a couple of examples. This is the URL as it's being produced by AUTOGRAM, so this is now a bit more. Now a bit more detailed. You find that AUTOGRAM can determine that the port is optional, the user info is optional. It's also able to abstract parts into path, such as path here. It's found out that this is actually a sequence of characters and digits. The host also matches a general expression. We have generalization rules in here. As soon as we have seen the same pattern occurring a number of times, we can come up with the generalization rule, and we check whether which generalization is the most appropriate one by figuring out if we generalize too far, we may have invalid inputs. So we try to find in this library of patterns, try to find the best matching ones. It also can infer more protocols. So and this is of course something that you can already put into a textbook, right away, because the names actually also are cute. The Java programmers did a good job in giving us good variable names. So this is URLs. Here's another example. This is ini files. We have key equals value pairs that come in individual sections. You find that all these parts as well are well identified. And here's a third example. This is JSON input. This is my favorite. This is actually the one recursive input because JSON is a recursive data structure. And here you find, well, what is a JSON? JSON is a value is an object, an array, a string value, true, false, null, a number. What is an array? An array is a square bracket followed by an optional value, followed by possibly even more commas and more values with a plus, with the closing array. All of this is automatically extracted. And if you extract such an input automatically, well, you can directly use this for fuzzing and fuzz plenty of JSON inputs. If you extract such a grammar from a program that accepts only a specific flavor of JSON, that is only a specific set of keys, for instance, then you can create a grammar that produces precisely this set of keys and therefore also is able to produce tests precisely for this input. If you go and test with such mind grammars, the way this works as follows. You have a set of inputs that you learn from, which you feed into, then you let them run through the program, we extract the grammar, and this is how we can then create tests, which gives you even more inputs, so there's a bit of a virtuous circle in there. However, there's one downside to the whole thing, because we depend on a set of inputs in the first place, and this set of inputs actually determines what the grammar eventually looks like. Such inputs, however, might not be available. And, of course, they always introduce bias, because you're not going to test anything that was not reflected in the inputs or a combination thereof. So we've worked hard on getting rid of this requirement, and we have introduced a technique we call sample-free grammar learning, which allows us to learn such grammars uniquely from the program itself. And we do so by introducing a test generator that creates such very inputs towards the program. But the problem is, however, that such a test generator is what we want to build in the first place. So we are in a chicken and egg problem here. We need a test generator to be able to build a test generator. But we can get around this problem by creating a test generator that is specifically targets the needs, specifically targets our needs of testing a parser, and this is called parser-directed test generator. And the way this works is, this is a test generator that specifically works to try to find as many parsing alternatives there are. The way this works is as follows. It does dynamic checks, namely by checking one input after another, again, how it is processed, but also including all the comparisons that are made on this value. Let me come up, so it starts with a random value, and this random value, actually that's a fixed input, is typically rejected because it's invalid, unless you're playing adventure or something. And what our parser-directed test generator does is it tracks all the individual checks that these characters go through. So it happens that the program here first checks whether the character is a digit. It checks for true and false. It checks for a beginning quote. And all these checks are not satisfied, which is why the input is rejected. So what we can do in the next step is, after tracking all these checks, is satisfying those checks. For instance, we can satisfy the check for a digit. This is rather trivial. Well, we feed it a digit, and it turns out that this is accepted. And next thing we do is we look at the other checks. well, this is fine. And we now check for, now we check for true and false. So yes, if there's a check for true and false, we give it a true, we give it a false, and these are also just as well accepted. And parser keeps on working, so next thing, the next check it did with the invalid input was it checked for an opening quote, and we send it an opening quote. Single opening quote doesn't work, this is rejected again. But again, every time the parser rejects something, we track all the comparisons it did before deciding to reject, and it turns out that it actually checks for a second quote, or it checks for a backslash, or it checks for an arbitrary character, which is again something we can trivially fulfill. So yes, it needs a second quote, so we give it a second quote. Here we go. So every time the parser rejects something, we check all the comparisons there are, and this is again rather easy to do. Don't need lots of big symbolic analysis for that. And this is how we can then explore one element of the grammar at a time by generating one test after another, and this is how we can eventually extract the entire JSON grammar. We have built this in a prototype for Python programs. Again, it's Python because we didn't want to focus too much on the technical infrastructure, but instead on the algorithms. And what this prototype is Pygmalion. This is from George Bernard Shaw, learning how to speak correctly. What we do have here, we have the program under test. We run the program with tests. We check the comparisons, and this gives us a set of inputs. Lots of inputs that cover all the features of the grammar, and we feed this into our grammar learner. And from the grammar learner, we get a grammar which we can then feed into a fuzzer. We have evaluated Pygmalion initially. We have compared this against AFL, a mutation-based test generator. We've compared this against CLI, a constraint-based test generator. And turns out, so Pygmalion runs a Python program. AFL and CLI, we have run them on equivalent C programs. We didn't provide seed inputs for any tool. CLI doesn't need seed inputs anyway. AFL heavily depends on seed inputs, as we very quickly found out. And well, we did all the way around, including the fuzzing. And it turns out that for one thing, this is very interesting, we get perfect coverage, meaning that each and every part of the program that can be reached through a valid input was actually reached. It was much faster than AFL. AFL creates lots and lots of random inputs and takes ages for AFL until it actually produces a valid input. And the structure of the inputs was also much, much better than what you would get from a symbolic tester like CLI. Just to give you an example, these are the longest inputs for a JSON parser that we got. Up here we have AFL. This is the longest input that AFL generated. It's a sequence of dots, which actually happens to be a valid input in the JSON parser we analyzed. This actually reflects your argument earlier on. I'm not sure whether a sequence of dots actually is valid, but well, this was accepted as valid input. CLI, this is the longest input that CLI produced. It has the characters NULL at the beginning, so it was parsed as null. That's fine. And this is the longest input that Pygmalion had, where you can see that we actually were able to explore plenty of features from the grammar. Yes?
Very quick question. For AFL, as far as I remember, they can allow you to enter some token types.
Yes.
So gradually you will also learn a grammar.
Yes.
Yeah. So when you run AFL, did you?
No, we didn't do that. We wanted to, because our aim is you have a program which you know absolutely nothing about, but still you want to be able to test this as well as you can. Sure, the more you specify, the more you model, the better you'll be able to test it again. But this all comes from exploring the knowledge that you at this point assume. In the very same way, I could go and write a grammar that allows me to explore all that knowledge, or I can pull off any of the great model-based techniques of software engineering. There's big books on that. As soon as I put my own brain power into this, I can do a much better job. But this brain power might need me weeks and weeks of work.
I see. Just a follow-up. I mean, I guess for each language, you only need to do this once, right? For JavaScript, you create a grammar once.
Yes.
For HTML once. So
Yes. That's actually a fun part, because once we do have a grammar learner for one language, and there's a parser in that language, then you can reuse the grammar for all other programs that use a similar input. So we could, for instance, the JSON grammar, which we learned from a Python program, is something that we can later apply to a C program, to a Java program, whatever. So once we do have the grammar, once you have the specification, there's lots and lots of things you can do with it. Okay, so this is Pygmalion, and these are the findings that we have. By construction, most of the inputs that we construct are valid. Grammars only cover the syntactic part. There's also a semantic part, which we cannot learn. Well, we could learn this principle, but then you would eventually you'd have to learn a context-sensitive language, or you'd have to learn a Turing machine, and then you don't want to program with it. In terms of combinations of inputs, we come up with lots and lots of combinations. So there's plenty of nice things, including giving you control over what you want to test, because of course you can also go in a grammar and say, I want to test this particular feature because all these features are named. You could assign probabilities to the individual parts. So there's plenty of possibilities in here. And yes, this is the first time that somebody has been able to pull a grammar out of programs without even having to provide any inputs. There's plenty of challenges, and I'm happy to be surrounded by absolutely great postdocs and students who work on this. Rahul Gopinath is the one who's currently working hard on building generalized grammar mining. Matthias Höscheler is the one who has been behind AUTOGRAM. Björn Mattis is working on dynamic tracking for C programs. Nicholas is building a fuzzer. Alexander is integrating this with a unit test generation. So plenty of folks around. We are working on extracting. So a couple of challenges we're having is implicit information flow is hard. If you have a generated scanners, say something produced by Flex, or a generated parser, Bison, Antler, you name them, then it's pretty hard for us to track individual characters through the parser because of the many comparisons that take place, including the characters being used as indexes into tables of scanners and parsers, and then the parser making decisions on that. That's a challenge. We need to find appropriate patterns that we can look for. We could also go and do general control flow dependencies, but in a parser, in generated parser, if you look at the code, you'll quickly find out that this is not going to work well. Parsers are great challenges for symbolic execution, by the way. Yes?
But generated parsers should be easy for you, right? You have the grammar.
A generated parser is not a primary target, because if you have a generated parser, then you typically also have the grammar in the first place, so extracting this could be trivially done. But generally speaking, the techniques that are used in generated scanners and parsers, which is mostly implicit information flows, these are techniques that we find challenging at this part. Okay? Context-sensitive features, we want to look for binary formats, identifiers, recognizing identifiers, checksums is also one of these. We're currently porting all this material to C, because in C there's actually far more programs available that process inputs character by character. Most Python programs that we work on simply are wrappers around equivalent C programs. So C is a more interesting target here. And finally, we are teaching this right now. So we are having a direct pipeline between what we build in our prototypes and what we teach. And I'm currently preparing all of this material in a book. It's called Generating Software Tests. And here also, I'd like to give you a short demonstration of how this works. This here is the book. It's called Generating Software Tests. And this is a book which actually covers all of the techniques that I know of that you can use these days for fuzzing and test generation. If you look up here, this is the current state. You have mutation-based fuzzing. This is AFL, fuzzing with grammars, grammar coverage, configuration testing, parsing inputs. Down here, mining input grammars. You also see the wrench. This indicates that this is a chapter in progress. And just for the fun of it, we can take a look into the fuzzing chapter up here. Here, this works. And this book is interesting because it comes with plenty of Python examples. And these Python examples, you can see them right away. You can execute them. You can see the output and everything. So this is plenty of fun. The most interesting thing about this book, though, is that that this book is actually generated from so-called Jupyter notebooks. And can I show you? Can you show you a demo here? Yes. No, you can't. Sorry. You can go and edit the thing as a notebook, which you can do right here. While it's loading, this is what this looks like. And here, in a Jupyter notebook, you see the very same text as the book, but you can now go into the individual parts and actually make changes to the program or add your own parts to the program and everything. So you can execute the whole thing at your leisure. So let me see. Has it loaded yet? Oh, here we go. Now it's live. So this happens right in your browser. You don't need to do anything. You just access the browser, and then the Jupyter environment starts in your browser. And here I can go. Here's my fuzzer. Let me go and define this thing. We import the whole thing. We execute it. Here we go. And now I can execute this thing. And here's fuzzer. Yes, this is great. I can execute this again, and every time I get another output in here. So I can run this. I can now go and assign this to some variable, and I can combine two variables in here, or can come up with arbitrary expressions. Let's come up with a longer string, for instance. Boom. And I can actually also experiment with the program. So I can go and say I want to figure out what's happening in here. I simply insert an appropriate command to see what's going on, and when I run the program right now, it actually prints out individual parts. So there's plenty of opportunities here for students to toy with the material and to put this all together. And of course, you can also import the individual modules and put them together nicely. And since I have a couple of instructors here, you will be happy to find out that there's also slides available. So all these are also automatically generated from the same input. And you can now go and show this off to your student and show off the individual parts and the results and all. If you go to a bit more advanced chapter in here, let's go to efficient grammar fuzzing. This is a big fuzzer in here. You will find that this actually that you actually can also come up with all sorts of visualizations in here. So let me see whether. Do I have something in here? Oh yes, sure. You can create derivation trees and watch them, how they work. So you can, for instance, see how this grammar fuzzer here takes a derivation tree and expands its derivation tree with each step. So all of this material is here, and you can also add some parsing and other material in here. All of this, this book will be published starting in 10 days from now. You heard it here first. And there will be one new chapter coming out every week. We'll start with the basic fuzzing stuff first, and then we'll proceed. Eventually we'll even get to symbolic techniques. We'll get to search-based techniques. All of this is nicely done in Python, and all the individual chapters should all be done by March, 1st of March. So it's like a Game of Thrones series, you know. Every week there's a new chapter, and at every end there's a nice cliffhanger. What will happen next? Oh, there you go. Will the fuzzer actually survive? Which character will die in the next series, and all that? Plus programs bleeding, dragons, everything. We'll have. Well, from a scientific perspective, of course, this is what we want to achieve. I'm sure we won't get the same audience, but maybe some level of enthusiasm. So, this was it, folks. This was it, folks. Parser-directed test generation and introduction to grammar mining. The Pygmalion package. We just submitted our report to archive. This was just yesterday. This will also be ready and released by the beginning of next week. So if you want to stay tuned, you can simply follow me on Twitter. This is @Andreas Zeller, and this will give you all the announcements in the next days regarding, regarding the mining techniques, regarding the book, everything. So enjoy. Thank you.
We can take some questions.
So with respect to the criteria for...
You can also stand up and simply raise your voice. That usually works.
Can you hear me? Okay. With respect to the criteria for the quality of the grammar that you produce, if I understood correctly, currently it's empirical. And my question is whether it's possible to formally verify that the grammar indeed satisfies the criteria that you want, or maybe even to formally verify that the fuzzer produced a good enough output in a formal setting.
That's a very interesting question. How good is a grammar actually? And to give you an example, simply finding out whether two context-free grammars represent the same language is already, if I recall it right, an incomplete problem. So just as a starting point, okay, because that's the problem we want to solve. And if you replace one of these context-free grammars with a program that accepts some input, you're not going to get better. You're not going to get better in terms of complexity. Yes, figuring out whether such a grammar is a good thing or not is what we do right now, purely empirically. But there are plenty of possibilities to tie such grammars and the knowledge that comes from such grammars into symbolic verification and into symbolic analysis. If you know that some part of the input has this particular form, and this goes into a string, you can get lots of assumptions on that string. If you know that this is a value that, if you know that this is a value of this particular form, if you know that this happens in this precise context, all of this gives you lots and lots of extra knowledge, extra contextual knowledge, which you can all use when verifying a program. Verifying a program in that sense may not necessarily, verifying a program, but checking whether the grammar you get is accurate for that program, is an accurate representation of the exact language. This is something where, this is an open question, which I'm not aware anybody has ever addressed. So there's plenty of work in there. But what I can tell you right now is that in almost all cases, a context-free grammar will not be a perfect representation for what the program actually accepts. Because a context-free grammar, by construction, is not going to take all the semantical constraints into aspect, is only going to focus on the syntax, and there will be a couple of features that simply will not be matched. Try to express a range of values, for instance, in a context-free grammar, it's not a perfect language for that. So it will always be an approximation. But the approximation should be good enough to be concise, to be well understood, just as all the other cases where we use context-free grammars for. And if it's good enough for that, it will also be a great match for testing.
Let's take a final question for Martin.
So I actually had a couple of questions, but I'll ask, follow up to this one, just so we stay. So I think in automata learning, there is Anglo-ins algorithm,
yes,
right? And that's meant to do like a bunch of iterative queries and give you the unique automata that you learn. So in grammar learning, I mean, you'd expect like a similar algorithm. I mean, of course, you have like positive examples, negative examples, querying the oracle and all this. So this would be, I think, what he's talking about in the sense of, here is I found a unique concept, which is the grammar, by generating positive, negative examples, queries with the users, generating inputs that separate two grammars, things like this. So I recall looking at this like a year ago or something, and there was like one theoretical work on this, but I have not seen it formalized, the comparative thing to Anglo-ins algorithm for context-free grammars. That would be the, I think, interesting thing.
So I have also, there's actually a field in formal languages which is called language induction, and there is quite a number of people who work on learning grammar representations or, well, automata representations from samples. This is the typical mode of operation. But this mostly stems from natural language analysis, because you have a natural language string and you want to figure out what is the grammar, what is the most representation for that. And it's also used for compression a lot. So if you want to compress things, it's a good thing to have a representation. But actually the tie between grammar induction or language induction on one side and programs on the other side, this is very much uncharted territory. And it's actually amazing that the problem of what is the input language for a program. Given a program, find out what the input language is. This is a question that could, in principle, have been around for 40 years, but apparently it's not one of the main. If you can solve it, you can solve lots of problems, but it's not in the canon it's not in the canon of challenges, and I assume it's not because until a couple of years ago, people did not have many good ideas on how to address this problem.
I mean, the program is the oracle in the Anglo-Instorm, so that gives you classification. So I think it could be phrased in this way. The setting is very different, I agree, but I think it could be phrased in this way. It can be very nice. I mean, this is very nice, but I think you could phrase it also as it would be theoretical, but it would tie very nicely, I think.
Okay, if you have more questions, Andreas will stay until late afternoon. Please go to talk to him. Yeah, let's thank Andreas again.
Okay, thank you.